And the topics for today: solutions, colloids, and suspensions, the solution process, and solubility. Solutions versus colloids. These are the properties of solutions. They're transparent, which means you can shine light through them. They don't separate on standing. They contain small particles, ions, and molecules that cannot be filtered and pass through semipermeable membranes. Colloids, on the other hand, have medium-sized particles. They can't be filtered either because the particles are still pretty small. They're on the size of up to maybe 10 microns. They can be separated by the semipermeable membranes, and they're less homogeneous than solutions are. Suspensions, on the other hand, have very large particles that do settle out due to gravity. You can filter them using filter paper. It must be stirred or shaken to keep them suspended. And examples include blood platelets, muddy water, and calamine lotion. Now, in this chapter, we won't interest much in suspensions, but I'm just throwing it in there so we can see a different type of mixture. Now, here's a table that lists different types of colloids. Now, the difference between dispersing medium and dispersed phase is the dispersing medium is analogous to a solvent. It's what the colloid looks like. The dispersed phase is analogous to the solute, and that's what's mixed into the medium. So if you look at the first one, for instance, an aerosol looks more like a gas, like the dispersing medium. And so we have fog or mist in aerosol. You can even say spray paint is like an aerosol. Solid in a gas, that could be like usually they're using smoke as an example. Here are some other types of colloids. We have foams, different types of foams, emulsions, a liquid and a liquid, solids and gels. The one thing about colloids is they don't have to be clear. Many of them aren't clear, like solutions are. And one thing about colloids and solutions, one way to tell the difference is by trying to shine a light through them. A light will pass right through a solution and the solution won't light up at all. But the colloid will light up. It shows the path of the light beam. And that's because the particles are big enough to scatter light so we can see it. Here you can see the light rays through the forest. And the reason we can see the light rays coming down is because they're hitting the dust in the air, just like you could see on a summer's morning in your own home. And now for a suspension, the particles are so big they easily scatter light. And here's a comparison of all three. So you should check this out when you're reviewing the topic. Now for solutions, we can have different types of solutions depending on whether we're mixing gases together, liquids together, or a mixture of different phases. Again, you want to note that the state of the solution will be the same as the state of the solvent, so the state doesn't change. Now these are some terms that you should know. Solute, the lesser amount; solvent, the greater amount. It can be milliliters or grams. Miscible and immiscible, liquids that dissolve in each other or liquids that don't dissolve in each other. Exothermic and endothermic. Exothermic means a solution that gets hot when you mix it together, when you produce it. Endothermic, one that gets cold. Saturated versus unsaturated. A saturated solution has all the solute dissolved in it that you can at that particular temperature. Now we're really talking about solids and liquids or gases and liquids for this. Unsaturated means you can still dissolve more solute. Supersaturated is when you start off with a hot saturated solution and you cool it. Instead of just showing some precipitation, it usually winds up becoming supersaturated, where you wind up with more solute dissolved than you usually can. Solvation is a process where the solvent particles bond to the solute particles. And when solvation happens with water, we call it hydration. Okay, let's take a look at the solution process itself. Now, in order for a solution to form, the solute must be more attracted to the solvent than it is to other solute particles. And also, solvent particles must be more attracted to the solute than they are to other solvent particles. So we have three different types of attractions, and we're going to look at them in terms of the energy effects. Now let's take a look at this chart here. So here we have the solute particles all bonded together. Step one would be to separate the solute particles, to expand them. That's going to take some energy to do that. So that process is endothermic. And then we have the same thing happening with the solvent. We got to separate them a bit, make room for them to mix together, and that process is also endothermic. Now, the third step over here is when they mix together and they kind of bond a bit together. That process is exothermic. Now, all we ever see is the sum of these three processes, endothermic and exothermic. Add all three together, and you get what we call the heat of the solution. So, if a solution gets hot, that means it was more exothermic than endothermic. If a solution gets cold, it means it's more endothermic than exothermic. Now, this is what hydration means here. Here we have an ionic compound, oppositely charged ions bonded together. And here are water molecules. Now, water molecules have partial charges on them, and they're attracted to oppositely charged ions. So here we have the positive end of the water molecule attracted to negative ions, and the negative end of the water molecule attracted to positive ions. And this up here is the result of it. Now you notice that the negative ions are surrounded by water molecules, where the positive ends of the water molecules are pointed in towards the negative ion. And down here it's the opposite. Here we have a positive ion, and so the water molecules orient themselves so that opposite charges will be attracting each other. This prevents the ions from linking back up and reforming the solid, this blanket of insulation that the water molecules are forming. Next thing we're going to look at is why do things like oil and water not mix together? And why do we need different solvents for different materials? So, two substances with similar intermolecular forces are likely to be soluble in each other. That means nonpolar molecules are soluble in nonpolar solvents. Now here's an example, carbon tetrachloride, nonpolar molecule in benzene, nonpolar substance. Polar molecules are soluble in polar solvents, ethyl alcohol and water. Ionic compounds are more soluble in polar solvents than in nonpolar. Our example here, sodium chloride in water, or ammonia. So now you can see what it means by like dissolves like. Polar dissolves polar, nonpolar dissolves nonpolar. Now ionic has charges, therefore it would dissolve in a polar solvent. Here's an example here of gasoline floating on water. We've seen this many times. After it rains, water on a road, and you'll see maybe it looks kind of shiny like that. And that's actually the gasoline on top. When the light hits the gasoline, the light rays get diffracted, and we see the different colors present. Now what's going on with the water molecule? Why is the water molecule polar? So here we have a little drawing of the water molecule. We have electronegativities, oxygen, hydrogen, and we subtract them to get the electronegativity difference, and that tells us that the bond is going to be polar. So we wind up then with two polar covalent bonds, oxygen to hydrogen, oxygen to hydrogen. And that's why our water molecule is a polar molecule. It has polar covalent bonding, and because of its bend shape, it has a positive and negative end, and that makes it a polar covalent molecule. Now, if we bring in other water molecules, we can see what can happen to them. They can bond with each other by forming hydrogen bonds. Now, a hydrogen bond is a much longer bond than the bond within a water molecule. These hydrogen bonds also are not nearly as strong as the bonds within water molecules, but they are important for the physical properties that water has. Water has a very high boiling point and a high melting point. Molecules that are as small as water usually have much lower boiling points, maybe like minus 100 degrees centigrade. Water also has a very high specific heat, meaning that it takes a lot of heat to raise the temperature of water. Now, if you think about it, when you're heating water, you're breaking these hydrogen bonds in the beginning before they can move around each other and have the temperature go up. That's why it takes so long to boil water. You're breaking hydrogen bonds that are present between some of the water molecules. And then when the water cools down, it reforms these hydrogen bonds, and that releases heat. So this is why water cools down so slowly. Now here's an example of oil and vinegar salad dressing. Oil is nonpolar, vinegar is polar. Which of these would mix with water? Turns out it's the vinegar. Why would the vinegar? Well, here's the acid that's in vinegar, and here's a water molecule, and you see how they can hydrogen bond with each other. And here's our hydrogen bond. Should hexane or methanol be used to dissolve grease? It's going to be the hexane. Why? Because they're both nonpolar. Now you notice that there aren't any oxygen atoms. Here's an oxygen atom in red. There's no oxygen atoms here for these two guys. All they're made up is carbon and hydrogen atoms. That's going to be nonpolar. What about vitamin A and vitamin C? Which one of these do you think would be water soluble? Which one fat soluble? Well, if you picked vitamin A to be fat soluble, you'd be right. So you notice this is very symmetrical, just carbon and hydrogen atoms here. Even though there's one low in oxygen, that means that it has an extremely low solubility in water, but still would be a little soluble, but it's much more soluble in fat. And then down here we have vitamin C, where all those oxygen atoms are bound to have a polar molecule, and vitamin C is water soluble. So because vitamin C is water soluble, you keep excreting it, and you have to keep taking it all the time. Vitamin A, on the other hand, if you take in that, that'll dissolve in the fat in your body. Then when that fat breaks down, it releases vitamin A. All right, so here are the energy terms of various types of solutes and solvents. So if they're both polar, what's going to happen? You're going to have a solution forming. Delta H would be small, meaning it might be a little positive or a little negative, a little exothermic or a little endothermic. Nonpolar, solute, polar solvent, no solution forms. Why? It's very little energy released when they bond together, and it lacks a lot of energy to separate the particles. So what we want to do is notice the ones that where solutions form. Solutions form here, because they're all large, and solutions form here. The energy effects are all small. And you notice then it's nonpolar with nonpolar, and it's polar with polar. Next thing we want to check out is the effect of temperature on solubility. We're going to look at solids and liquids and gases and liquids. So here's a chart that almost every chemistry text has. This would be a figure probably 12.6 in your book. So let's take a look at it, what we have here. On the left we have the solubility, which is measured in grams of solute per 100 grams of water. So these numbers here are all grams of solute. And then down here we have the temperature increasing as we go from left to right. You notice that most of these compounds are more soluble in hot water than cold water. There are some exceptions. Sodium sulfate is more soluble in cold water, and so is cesium sulfate. Generally, I think we can say if you increase the temperature, you'll increase the solubility of most solids in water. That's why we dissolve a lot of things in hot water rather than cold water. What about gases in water? Well, it's just the opposite. And gases are more soluble if the temperature is lower. So warm water then has less gas dissolved in it than cold water. Carbonation. Well, carbonation is dissolving CO2 in water. We can see here the gas bubbling out of a bottle of Pepsi. Now CO2 is nonpolar, water is polar. So there's not going to be much dissolving as it is. So how did they force the CO2 to dissolve in water? And the answer is pressure. Now here we can see that if I want, this is supposed to represent CO2. If I want to get that CO2 to dissolve better in water, it dissolves a little bit, but it's the same number of molecules that are leaving the solution as are entering. How can I get more to enter? I can decrease the volume to increase the pressure. And thus I wind up with many more gas molecules dissolved. And that's how they actually make CO2 dissolve in water to make soda water. Now instead of decreasing the volume, what we do is we increase the pressure by just adding more CO2 above the solution. And there's actually a gas law for this one. It's called Henry's law. And Henry's law says that the solubility, which is represented by C here, the solubility of a gas in water is directly proportional to the pressure of the gas above the liquid. So the more pressure you use, the more soluble the gas will be. When they make CO2, when they make soda water, that is, they usually use anywhere from probably 5 to 10 atmospheres of pressure of CO2 of the liquid. That's way, way more than you find happening in the air. Now K down here is called Henry's law constant, and we would just use that in our formula. And that's the end of the show for today.